This is a video on the topic of motion as part of the Year 10 science curriculum. Okay, so motion relates to the area of physics. And so I thought I'd make a video on just a brief summary of the topic, the main ideas. So I'll start off with Newton's laws of motion. Okay, the fundamental basis of any physics course that you do, any introductory physics course that you do, is Newton's laws of motion. It's called classical physics. It falls under the umbrella term of classical physics. So the physics of scientists like Sir Isaac Newton. So Sir Isaac Newton came up with these laws in the 1600s, among other things. And they can be stated as follows. So the first law is also known as the law of inertia. And it states that an object in motion remains in motion, or an object stationary remains stationary unless, it's getting a bit messy here, unless acted on by an outside force. Okay, this is the best way I can define it in layman's terms, simple terms. An example, well, suppose you've got a car that's just sitting there, stationary. There are no forces acting on it, okay? And suppose you have another car driving along at constant speed, it's called a V. These two scenarios are Newton's first law of motion in action. Inertia, by definition, is the property, I should say, an object's resistance, object's willingness to resist motion. What does that mean? Well, think of an elephant versus an ant, okay? An elephant has more inertia than an ant, okay? It's more resistant to motion, okay? It's bigger, it's heavier. I get asked this a lot by students as well. Suppose you've got a car moving along, let's say it's moving along at constant speed along the road, and you've got, let's say, a pair of glasses at the back, on the back seat. Let's say, well, I should say behind the headrest, let's say, at the back of the car near the window. Let's suppose you slam the brakes all of a sudden. What would you observe? Well, when you slam the brakes, you will continue moving forward slightly, okay? So I'm just exaggerating the photo here. Let's suppose this is you prior to slamming the brakes, then all of a sudden you experience this sensation. That's because your body isn't strapped on completely, okay? So you've got a seatbelt that's just there to keep your main part of your body secure, but your head sort of goes forward a bit and moves forward. And the glasses will fly forward, okay? Would hit the windshield if they're not secure, the front windshield. Why is that the case? Well, because you and the glasses want to continue moving at that constant velocity, okay? You can think of it as like a delay. So that's why. You move forward a bit and the glasses move forward, because according to Newton's first law, everything wants to remain in that state of motion. Newton's second law is a simple one. Okay, it can be defined mathematically. Best way I can define it as a physicist, you need a force to move something. Best way I can define this second law. You need a force to move something, whether it be a push, pull, twist, throw, ... Okay, F stands for force, and force is measured in units of newtons in honor of Sir Isaac Newton, capital N. M stands for mass. Okay, it's got units of kilograms. Okay, small k and small g. I've seen students write capital K, that's wrong. And A is the acceleration. Okay, it's got units of meters per second squared. Just a little detour here. Why is it meters per second squared? So acceleration by definition is the change in velocity with respect to time. Okay, it's the rate of change of how fast you're going. So the numerator this top bit, delta V. So delta means change in, which is just, we can just write it as V sub F minus V sub I over T sub F minus T sub I. Okay, the difference between the final initial velocities and times. The units for the numerator velocity is just meters per second. Units for time is seconds. So therefore you get meters per second squared. Okay, because there's 2 seconds. What are some examples of F equals ma? Most obvious one is that of a car. Okay, you need to apply a force to get a car moving. Okay, when you put your foot on the accelerator pedal, that's causing a combustion reaction in the engine, causing the wheels to rotate. Let's say playing cricket, when you whack the ball, that's a force applied to the ball, etc., etc. Okay, Newton's second law of motion. Newton's third law of motion simply states that for every action, there's an equal and opposite reaction. Favorite example being an aviator, aircraft. Okay, here's an engine, another engine. So aircraft, their engines produce thrust. Thrust is a force. Another word for force. Thrust acts this way, backwards, towards the back of the plane. So thrust, and you get propulsion forwards. Okay. The action is thrust. Reaction is the propulsion. Okay, same thing with a rocket launch, rocket taking off. Okay, thrust, propulsion. I get asked this a lot by students as well. If forces are equal and opposite, how can an object move like an aircraft? Good question. Let me explain why. Okay, so an object can move even if it experiences equal and opposite forces through a concept called net force. Net force. Net means total. Okay, the net force acting on an object is basically the sum of all the individual forces acting on it. Okay, if the net force is non-zero, the object will accelerate in the direction of the net force, according to F equals ma. I'll give you an example. This is a classic exam style question. Suppose you got an object, okay, some mass weighing in at 5 kilos. You've got a force acting in from the left, 20 newtons, and another one, 10 newtons. Notice how I've drawn the arrows. One's longer than the other because length of an arrow, okay, a vector in this case. A vector is something that's got size, so 20 newtons and direction, which is acting to the right. Vector's got size and direction, so the bigger the arrow, the bigger the force. Suppose I've got a force 30 newtons acting towards the left. Okay, in this case, if you were to find the sum of all forces, what you do is, so you take the 20 newtons plus the 10 newtons and you subtract 30 newtons. Why do you do that? Well, we're taking the right direction to be positive, left direction to be negative, okay? Just chosen these two arbitrary directions to be positive and negative. 20 plus 10 is 30. 30 minus 30 is just 0. So in this case, the net force, the total force acting on the box is 0. Right? And so if you were asked in this question, let's say to find A, the acceleration, what would you use? You would use F equals ma and rearrange. So the first step is to use, in this type of problem, use F equals ma, write it down, rearrange for A, algebraically. The total force, we just found it, it's 0. And we know that anything 0 divided by something else will give you 0. So the acceleration is 0. Now, when an object experiences equal and opposite forces, the forces may cancel each other out in terms of magnitude, in terms of size, but they can still result in a net force if they act in different directions. Okay, in this case, the object will accelerate in the direction of the net force. Okay, so let's say the aircraft here. Let's have the aircraft. Okay, they can be equal and opposite in magnitude, but not in direction. That's why an aircraft can move forward in the air. Another example, suppose you've got a book. So here's a table. Here's a book on a table. Now the force of gravity pulls the book downwards, while the normal force acting upwards exerted by the table pushes it upwards. And these two forces have equal magnitudes, but they act in opposite directions, okay? So the net force on the book is 0, since they cancel each other out. And so the book remains at rest, okay, in this case. However, if there's an additional force applied to the book, okay, if someone's pushing it horizontally, let's say this way, the net force becomes non-zero, okay? So it's not equal to 0. And the applied force, in this case, and the force of friction acting in the opposite direction, they may have equal magnitudes, equal size, but since they act in different directions, the net force is given by the vector difference, the difference between the two forces, the two directions. Okay. And so I think that's it for motion. Distance, time graphs, all those other types of graphs I talked about in different videos, but these are the main ideas. And these, so Newton's laws of motion, it's all about application when it comes to exams. Okay, so understanding how it works like this should be sufficient.